Hello. Good morning all. In this class, we'll discuss about balancing of rotating masses. So first, we'll try to understand how we are doing balancing of these masses, rotating masses. Suppose if you have suppose this high speed of engine and other machines is uh, common nowadays. It is common. And suppose if you want to balance this reciprocating and rotating parts, okay. Now to get that balancing of that rotating masses, what we have. First, we need to consider distribution of that mass. Okay, so distributed masses are supposed to say m1, and balancing masses which we are adding, that are supposed to say m1 and m2. Okay, so m2 is the balancing mass for m1. So these masses are rotating about the axis of rotation. So look at the r1 radius of we can say radius of mass m1 about the axis, and r2 is the radius of balancing mass m2. Now it is providing impact of that centripetal force. That centrifugal force we need to calculate by using that masses m1 and m2. So we can write centrifugal force acting on that mass. Okay, centrifugal force will be m2 m r omega square. So basically, we are taking that balancing mass m2, r2 will be the radius for that mass, omega is the angular speed or angular velocity, we can say. So you can write m1 r1 omega square, because we need to balance the mass m1 with mass m2. So I can write m1 r1 omega square will be m2 r2 omega square. So omega is having same speed of rotation, so it will get cancelled. So we have m1 r1 is equal to m2 r2. Okay, so balancing of single rotating mass, if we consider by two masses rotating in different plane. Now in previous case, we are balancing same single mass m1 with mass m2. But suppose if we are balancing single mass m1 with two different masses. Okay. Now just look at the arrangement, how that centrifugal force is acting when we are taking balancing of masses of m by taking two distributed or different masses m1 and m2 for distributed mass m. Now we have L length between two plane L and M. L1 will be the distance between plane A, okay, and point D, point L. L2 will be the distance between plane A and M, okay. So we have this mass M, and we are taking balancing masses M1 and M2, having radius of curvature R1 and that rotations R1 and R2, okay. So look at the centrifugal force acting on this mass. It will be Fc is equal to total centrifugal force will be Fc1 plus Fc2. Okay. So again, centrifugal force we can write mr omega square, which is m1 r1 omega square plus m2 r2 omega square. Again, omega will get cancelled out. So we have mr is equal to m1 r1 plus m2 r2. That are the correlation between centrifugal force. Okay. Next part is, so if we are correlating same part with respect to that length L and L2, so you can write FCL is equal to FCL2. Just look at the previous slide. So we have this mass FC, and we are taking that centrifugal force about this part. So FCL is equal to FCL2. That is the moment about that centrifugal force. Force into length is nothing but moment we are taking. So again, we can write Fc m1 r1 omega square into L, and Fc will be mr omega square into L2. So we have this correlation m1 r1 L1, m1 r1 L is equal to mr L2. That we can write m1 r1 is equal to mr L2 by L. That is first part. Similarly, we can write second part, Fc2 into L is equal to Fc into L1. So put that value of Fc 2 m2 r2 omega square into L is equal to mr omega square into L1. Again, we have m2 r2 L is equal to mr L1, or you can write m2 r2 is equal to mr L1 by L. Okay. Now suppose if you are taking when the plane of distributing mass lies on one end of the plane of other masses, that is balancing masses. So you can write L1 L, that is the L M1 is on this side, and we are balancing mass M2 and M, distributed mass M in other side. So again, we can take radius R1, R2 is the radius of that balancing mass M2, then M is the distributed mass. So again, we can define correlation. Fc is equal to Fc2, centrifugal force of distributed mass is equal to balancing mass Fc2. Fc plus Fc2 is equal to Fc1. So we can take mr omega square plus m2 r2 omega square is equal to m1 r omega square. So omega will get cancelled out. So mr plus m2 r2 is equal to m1 r1. So again, we have fc1 L is equal to fcl2. So m1 r1 omega square L is equal to mr omega square, that is L2. So again, we can write m1 r1 is equal to mr L2 by L. Okay. And fc2 into L is equal to fc into L1. Again, we can there are second correlation, that will be m2 r omega square L mr omega square into L1. So we have second correlation for mass M2. M2R2 is equal to mr L1 by L. Okay, so in this way we can determine this part. Now suppose if we are using a graphical method, okay, to determine that balancing of masses, again we can apply this concept. So we have a space diagram where we are determining the orientation of fc1, fc2, fc, resultant force fc3, fc4, and fc, distributed mass. So we have angles theta 1, theta 2, theta 3, theta 4. Okay. And radius are R1, R2, R3, R4. So just we have to determine, we have to just mark the each and every location for that vectors. Okay. So you can write FC1, just draw FC1 and its magnitude angle, then draw FC2. This is the second orientation. Then FC, we have third orientation with theta. Then FC4, we have fourth orientation and its resultant. Okay. So by putting all this, one can determine the resultant uh, centrifugal force acting on that particular system, that we can determine. Okay, and by analytically again we have some equations. Okay, by using that analytical method we can write sum of horizontal force, that is horizontal component of centrifugal force acting on system will be m1 r1 cos theta 1 plus m2 r2 cos theta 2 up to the last part, and vertical component acting on plane will be m1 r1 sin theta 1 plus m2 r2 sin theta 2. Okay, so one can determine the magnitude of resultant centrifugal force acting on the plane. So it will be Fc horizontal force plus vertical force, summation of horizontal force square plus summation of vertical force square. So if theta is the angle between that, the resultant force which makes an angle of horizontal plane, then we can write tan theta is equal to summation of vertical force upon summation of horizontal force. And again, suppose if you want to calculate magnitude of balancing mass, then again you can use, because resultant is centrifugal force Fc. So you can equate that centrifugal force is equal to mass into radius, and based on that, one can find out the magnitude of balancing mass. Okay, in this way, we can calculate all these process for rotating masses. So this is very simple part. One can use the first we need to understand how that mass is kept and what are the orientation of that mass. Suppose if you are using single mass like mass m, then for mass m1 we have balancing mass m2. This is only we are using single distributed mass and single balancing mass. Similarly, we have second case where we have one mass, single mass, and for which we are using two distributed masses. Okay, again these two distributed masses are in different plane. That was first case where we are determining centrifugal force acting on a plane, and second case which we have discussed, that second distributed mass is acting towards the that balancing mass. So this is the distributed mass, and this balancing mass is acting in the orientation of your distributed mass. Again we can determine correlation of centrifugal force acting on second case. Okay, so in this way we can identify the overall centrifugal force, resultant force acting on that masses. Okay, so this is all about balancing of rotating masses. We'll stop here. Thank you.